coding. Anyway. Okay, so this kind of thing is called linear combination. So one of the results we have for the general linear ODE is that a linear combination, if you have y1 and y2, then you've got a whole bunch of solutions. Not just a whole bunch, an infinite number of solutions. Okay, because C1 is an unspecified constant, C2 is another unspecified constant. So you've got an infinite number of solutions. But it's okay, right? You have experience in the first order ODE already. So infinite number of solutions is quite natural in differential equation solving. 有无限多个解，事实上是非常非常自然的一件事情啊。OK， 你最好要有，你要是没有呢，才是一个大麻烦了，对不对？ Because we need to put in the initial condition. You need to specify the initial condition to get a path or a solution of the whole physical problem. Therefore, this C1, C2 is not a problem, it's not a pathology. Actually, C1, C2 is just there for us to fix to fit the initial condition of y1 prime and y1 and y at a certain time. Usually we choose the time at the beginning of t equal to 0, but it's okay if you want to choose other time, for example 1 second or 2 seconds. As long as it's a fixed time, it's the position and the velocity at a certain time, then it's okay. It's a valid initial condition. But usually we choose t equal to 0, t equal to 0 for the initial condition. That's why it's called initial. Okay, from the beginning means from the beginning. Okay, so these two facts we haven't do it. We did it last week. You can see that again. If you got a y1, then you get a y2. If you get a y2, then you get a whole bunch of it. And if you go whole bunch of it, then fix the initial condition and you are done. Okay, so it's really powerful. It's really powerful. But as long as it is powerful, it probably is not that useful. Okay, because it's simple. You need to have one solution in the beginning. 你一开始至少要有一个解啊。Okay, so that's the restriction. That's the restriction of this powerful mathematical theorem. You need at least one solution to start with to solve the equation. But sometimes it's not that easy to get that one solution. Okay, that's why this method, sometimes called Brownian method, or sometimes by other name, is very beautiful and powerful, but not really that useful. You probably won't encounter this kind of thinking in the next couple of years. Okay, so this week we are going to, in the following, we are going to restrict the subset into an even smaller subset. We call it linear ordinary differential equation with constant coefficient. A second order linear differential equation with constant coefficient. Let me go back to where I introduced this. Now, so if you again, that's the equation we are talking about, linear. But we can restrict this equation to an even smaller subset by restricting px and qx to two constant, a1 and a0. Okay, so because the coefficient is a constant, so we usually call it ordinary differential equation with constant coefficients. For these kind of linear equation, actually we have a systematic procedure. I'm going to show you next week. We have a systematic procedure using complex number to write down the solution. Okay, and almost 90% or even more, the differential equation you are going to encounter in college is in this form. Okay, 在你大学的时候你会碰到的大概就长这样。Okay, so that's why it's useful, because that's actually what you are encounter most often in your college study. Okay, Okay, so next week, we are going to concentrate on second order linear ordinary equation with constant coefficients, like this one. And you will see that this kind of systematic method not only apply to the second order, it could be applied to any linear ordinary equation to arbitrary order n. Okay, so that's how powerful this method is. We call it complex number method. Okay. Now, in this class, we usually like to illustrate the mathematical abstraction by a physical example. Okay, you remember in the first order equation, we use decay equation and the projectile motion with air resistance. For the second order equation, we are going to use simple harmonic motion. 简谐运动. Simple harmonic motion means you attach a mass or a particle with mass m to a spring with constant, the force constant k. Okay, so that means for this particle, the force it experience equal to minus kx. Is that okay? So this is called simple harmonic motion. Oh, you think harmonic? Why? Could I hear anything? No. Okay, so this harmonic doesn't mean it's a sound-producing thing. No. Device. No, it's not. But however, from very old days, even Greek know that harmonic, when the sound is harmonic, beautiful, that means it is a periodic motion. So in physics, when we say harmonic motion, we usually means periodic motion. So that means it happens again with a constant period. Okay, so whenever you see this word harmonic, probably you need to pop out periodic in your mind. Okay, so the simple harmonic motion means the simplest periodic motion. Sometimes this kind of motion it is oscillating because it's oscillating. 震荡. Okay, so sometimes we also call it simple harmonic oscillation, abbreviated as SHO. And for the former simple harmonic motion, I abbreviated as SHM. So whenever after this point, when I say SHM or SHO, you better know what I'm talking about. We're talking about this. Okay. 简谐震荡, 简谐运动. Okay. In Chinese. So the equation of this, the equation of motion of this simple harmonic motion is quite simple. So if f is equal to minus kx, then f equal to ma tell you m times x. The second derivative of x is equal to minus kx. Okay, so it's obvious that maybe here. Usually we like to divide the m and move the m from the left hand side to the right hand side, and then you will get x dt squared equal to minus k over m times x. And usually we would like to abbreviate this k over m with another notation. We call it omega. Of course, you have done general physics already, so you know this omega is angular frequency, right? Okay, but it will appear later. At this moment, this w is only a constant. Just a constant. It's an abbreviation notation for square root of k over m. Is that okay? So this equation could be written as here, dx dt squared. Oh, I don't know. Yeah, the battery is not high enough. So I'm going to stop using this. I forgot to charge yesterday. So I probably need to speak louder. So if you could not hear me at the back, tell me. Okay, let me know. Okay, so this is the equation of motion, or the second, and of course, it's easy to see it is second order linear ordinary differential equation with constant coefficient, because omega squared is the constant, okay? And also, because on the right-hand side, it is a 0. There is no function fx. In this kind of case, we also call it homogeneous. Remember, in decay equation for the when we talk about decay equation, when we talk about the projectile motion with air resistance in the horizontal direction, dvx over dt equal to minus b over vx. Okay, so if we move this to the right hand side, again on the right hand side there's nothing. Okay, we also call it homogeneous. But when we move the discussion to the vertical direction, dvy dt, because the vertical motion dy has a gravitational acceleration, right? 有重力, 有 gravitational force. So there is a term on the right hand side. So we call it inhomogeneous. Okay, and here is the same. Because that on the right hand side it is equal to 0. That means fx is equal to 0. So we will call it homogeneous second order linear equation. Okay? This distinction is very, very important because very soon I'm going to add a term which made it into inhomogeneous. And the relation between the two solutions, that means the solution of this and the solution of this, the solution of this with this inhomogeneous solution, homogeneous version will be very, very strong. You will see very, very soon. And very, very useful relationship. Okay? So now, just remember the terminology, homogeneous. Before we go into detail of actually here. If I add another force, if this system, this oscillation is exerted external force, for example, I want to force the oscillation to continue without stop, then I probably will put a rotator, for example, at the other end of the spring, so that this guy will exert a force, usually a periodic force, to the system. Okay, so that means on the right hand side you need to add another term to represent an additional force. Usually we call it F0 cosine omega dt. We'll go into detail later and give you some example. But at this moment, just think about it. If I add a term like this, external force, just like we add a rotor here to exert the external force, then the equation of motion will become this. Okay, and then the right hand side, Fx is not 0. It's a source. So that's why I told you that this kind of term are called source term, because it's the source of an external force. Okay, yeah. So this is the inhomogeneous version of the homogeneous version. Okay, corresponding to the homogeneous version. So you will see very soon that the solution of the two kinds of differential equation are closely related to each other. Okay? Now, let's start to solve the equation. So my procedure is very, very simple. We started, any question now? We started with the simple harmonic motion, and then we add a damping. Both of them will give us equation of motion homogeneously. Okay, but then I will add the external force. The external force will make the equation into inhomogeneous differential equation. It's okay. All three cases correspond very strongly with phenomena in the natural world. Okay, so that's why this kind of discussion, maybe you have already learned it from the general physics. But in general physics, usually professor will emphasize the phenomena. But here, I will emphasize the technique, how to solve them. Okay, but in today's discussion, we usually call it method 0. Method 0 means we solve it by intuition, 用直觉去解. Okay. Next week, I'm going to present a systematic way to solve all these three cases systematically. That method could be extended to arbitrary order of differential equation. Okay, so method 0 today, method 1 next week. Method 0. So we are going to solve, before we do method 0, let me emphasize how important different simple harmonic motion is in the physical learning. You may see, why should I care about a spring? I never see a spring in the laboratory, right? Okay, but remember, this is simple harmonic motion does not just happen in this kind of spring mass system. It also appears in any kind of state, any kind of problem with stable equilibrium point. 只要你的问题里面有一个稳定的平衡点 ，in case there is an equilibrium point, then any small motion around the equilibrium point is a simple harmonic motion. 任何一个在平衡点旁边小范围的运动都是简谐运动。If you do not believe me, then let's take this as an example. Let's take atomic force as an example. Atomic force is the force between two atoms, and if we separate them by a distance x, then this atomic force will be a function of x. We will write it in this way. And according to experiment, the magnitude of the force can be written in like this diagram. The horizontal axis is x. The vertical axis is the magnitude of the force. Okay, so you can see that when they are separated far away, then atomic force is almost zero. But when they come closer and closer, the force is negative. Remember, negative means the force is in this direction. So it is an attractive force. Atomic force is usually an attractive force. However, when the two atoms comes too close, then part of the electron's structure will overlap. Remember, all electrons are of the same charge, same type of charge, negative. Therefore, they will repel each other. So again, when the two atoms really close, so that the atom system repel each other, then this atomic force becomes positive. Again, if it is positive, that means the direction of force is in this direction, and so it's repulsive. It's okay? 好，所以呢 ，let me do it in Chinese. OK， 假如这个原子力呢是负的，那就表示它是吸引力。所以两个原子一开始的时候基本上是吸引的，互相吸引的。OK， 好，那当然了，远的时候就没有了，好，力就越来越小，as you expected。但是呢，如果越来越靠近的时候，两个原子的系统电子呢会互相 overlap。那电子跟电子是互相排斥的，所以呢，当两个非常靠近的时候，它就变成是一个 positive 的排斥力。OK， 好 ，positive 的排斥力 ，is OK？ So between positive and negative force, there must be a zero, right? Exactly. So there must be a point where the force is equal to zero. Everybody, let me introduce the equilibrium point. 第一次见面，平衡点。So this is the equilibrium point of atomic force. Okay, so if there is an equilibrium point, that means if you put the two atoms at exactly the equilibrium point, they will move. There's no force, they won't move. However, if you push them together a little bit, like this line, the blue arrow, we push them a little bit, then the force will become positive. Again, positive force means repulsive. That means the direction of force is this red arrow. So obviously, this atomic force will push it back. Think about it. When you push it away, push it closer, then you push back. And you can do the reasoning again if you consider we separate, pull them out. Then pull them out, the atomic force becomes attractive and will push them back. That's exactly the thing a spring will do, right? 这 exactly 就是一个弹簧会做的事情啊。So everybody, when around the equilibrium point, the atomic force look like a spring. 原子力就好像是一根弹簧一样。Okay, so this is not just in qualitative way. Quantitative, it is also true. Geometrically, it's so clear. Here, if I magnify this small area around the equilibrium point, it is obvious at this equilibrium point, the force line, no, it's curved. But if the motion is concentrated of small area, then this curved line becomes straight. 曲线就变直线了。Okay, so if it is a straight line, that means it is actually a spring system, right? 因为呢 the hook law will apply at a very, very small area. I hope it makes clear to you. Near the equilibrium point, the force line can always be approximated by a straight line. In this diagram, the red line is the curved force line, but it could be approximated by this dash line, which is straight. Okay, so that means in a small area, the atomic force look like a spring force. So you don't need any convincing to believe that it is actually a simple harmonic motion. Okay, if there is an equilibrium point, then there is a simple harmonic motion. Remember, the above argument does not rely on the detail of the whole atomic force. Any kind of equilibrium point could be applied. It could be applied to any kind of equilibrium point. Okay, it could be an atom inside a solid. So that's why you always see this kind of diagram. We put the atom into a lattice. When we say we put the atoms into lattice in a solid, we means the force between them looks like a spring. Okay, so you probably see this kind of model. Okay, in kindergarten. Okay, it's solid. And also, this only applies to solid state physics. Any kind of equilibrium point, it could be a pendulum. It could be some ball oscillating in this kind of wedge. And remember, every time there's an equilibrium point. It could also apply to a transfiguration or changing of shape. I call it because the original shape of a solid is by definition a stable equilibrium point. For example, Taipei 101 or any kind of bridge. When there is no vibration, it's an equilibrium point. But if it is blown by wind, earthquake, whatever, it starts to vibrate. That means it deviates from the equilibrium point. And that deviation, that small motion, that vibration is a simple harmonic motion. Any kind, any equilibrium point. See? So you learn it once, and the result could be applied to all these questions. Isn't that powerful? Okay, so that's a powerful characteristic of the mathematics thinking in physics. Because again, do it once, and you could use any time you encounter a similar equation of motion. 好，所以呢 ，in Chinese， 所以所有的这些问题，它其实都有一个平衡点，都有一个平衡点。那只要你在平衡点附近呢，做一些小小的变形，不管你是因为呢地震，不管你是因为风吹 ，whatever reason， 你开始有一点点的这个偏移，那个偏移都是 simple harmonic motion. Apply to all of them. Apply to all of them. Okay, so I hope you all. And in some of the transparency, I'm going to skip because it corresponds to more detailed discussion. You see the a gray background, that means I didn't cover it in class. OK， 好，所以你如果看到后面是这个 gray 暗灰色的这个灰色的这个背景，好，那就表示呢，它就是我们在课堂上面没有讲的。好，但是呢 feel free to study them because that's sometimes may be useful for your future. Okay, and here I say almost everything corresponds to a spring in the nature. Even a fundamental particle corresponds to spring. for example, electron, neutrino, quarks, anything are a spring. Okay. So, in a word, our universe is made of spring. Okay. Yeah, and simple Hammond motion even apply to this kind of circuit, LC circuit. Okay, so it's a standard topics in general physics. Oh, second semester, so probably encounter this kind of calculation in high school. If not, Professor Liu will cover it very soon. It's called LC circuit. And in this kind of LC circuit, we couple a capacitor with inductor. 这样子就电路叫做 LC 电路。我们把电容器呢跟电感器把它连在一起。And you will see that the equation of motion, not, I shouldn't call it equation of motion because there's nothing moving.
什么是电容器跟电感器？
嗨 ，Wait till Professor Liu， 你们的老师是刘祥林老师嘛 ？Yeah，Wait till Professor Liu cover it. 电容器 means just two plate, metallic plate. Okay, and then it's called 电容器. And the point of a capacitor is that you can store electric field in between. 你可以把电场藏在这个中间。There is no electric. No, it's not battery. 不是电池，它就是两片。But you can charge it. You apply a charge, a voltage difference between them, then there will be electric charge on the plate. Wait, probably another 1 month, Professor Liu will cover capacitor very soon. So you don't need to care. So it's great. So you haven't encountered this topic before, you just ignore it. But one thing I want to emphasize here is that the same kind of equation even apply to this kind of electric circuit. 我要强调的是，同样的方程式，连这种电路学都会有用，不见得只是运动。刚刚前一页是告诉你，所有东西的变形都是 simple harmonic motion， 但是 simple motion 的 apply 的范围甚至比这个还大，就算是 LC 电路，它都是一个 oscillation。OK， when this oscillation occur, let me show you the result before the Professor Liu told you. The result is that the Q, the charge on top of the metallic plate, will oscillate just like a spring with this kind of function, oscillating function. And if Q is like this, the current will be like this. If current is like this kind of device will emit electromagnetic field, 发出电磁波. So it's actually an antenna. This is an antenna. 就像你听广播的时候，它发出来的电磁波，就是像这样子的一个 LC circuit 所发出来的。Okay, I'm ahead of your study. So probably in about 1 month or 2 months, Professor Liu will cover this. You will remember, yeah, Professor Chen also told you about capacitor and inductor. Okay, 好，别着急。Any question? Very good. If there is any response, I appreciate it. 尽量问啊，什么样的问题都可以问啊。In Chinese or English, okay. 好 ，Now back to the main topic. Maybe I should use this microphone. Just a minute. Let me untangle this. Oh, okay, so it's good. Okay. Otherwise, I won't be able to last 3 hours of talking. Any question? So enough for telling you how important simple Hammond motion is. Now let's get back to business. Let's solve the equation. That's our main business today. So the equation is like this. I've told you already. Ma equal to minus kx, and then if we move the m to the right hand side, it becomes minus omega squared. We use a new notation omega to designate the square root of k over m. But that's very important because I haven't solved any equation yet. But simply by writing the equation in this form, we got some very important result. That is, a simple harmonic motion is completely determined by this number omega. Put it another way, any simple harmonic motion with the identical omega has the identical solution. Okay, you can double k to twice, m twice, but if omega is the same, then the solution will be the same. So omega, we usually call it the characteristic constant of a simple harmonic motion. Okay, so every simple harmonic motion has a omega. Okay, has a omega. Its own characteristic property. Omega. Okay. Now it is obviously a homogeneous second order linear equation. I have told you already with constant coefficients. I'll just compare this to here. Of course, we only have the first term and the third term. Later, very soon, in about 20 minutes, or maybe 15 minutes, I will add in the second term, and it will look like this. Okay, let's solve it first. This equation states that, usually because it method 0, so we are not doing it systematically. Okay, 直觉的啦, So let's look at the equation for a second and think about what it means. It means it states, you make a statement that the second order, the second derivative of x is proportional to itself. It's almost like the decay equation, right? Remember in the decay equation, we say it states that the first order derivative is proportional to itself. Okay, so now we are upgraded to a second order, but the equation itself are quite similar. The second order derivative of x is proportional to itself. And by the same intuition, we know polynomial couldn't fit because every derivative will lower the order of the monomial by 1. X to the nth power will become x to the n minus 1 power. So when you do two derivatives, that means you will lower the order of x by 2. And it could not be proportional to itself, right? So polynomial couldn't work. Maybe exponential function, which is the solution of decay equation. Maybe it will work, but still no. The reason is the negative sign here. Remember, exponential function is the solution of decay equation. So the derivative is proportional to itself. So if you take the derivative twice, it is also proportional to itself, but with a positive proportional constant. In Chinese, 这个指数函数呢，如果你做一次微分，就变成跟它自己成正比。那照理讲，做2次微分也跟它自己成正比啊，但是那个常数是正的。But here the equation is negative. Okay, so because of this negative sign, the exponential function couldn't fit either. Okay, so we rule out polynomial, we rule out exponential function, but of course everybody knows the answer. Sine function could fit, right? Because sine function, when you make derivative, it becomes cosine, and cosine, when you make derivative, becomes minus sine. And then minus sign account for this minus sign here. Is that okay? So intuitively, you immediately can guess an answer, one answer to this equation. That is, a sine function will fit this equation, will satisfy this equation. Okay, so let's do the calculation directly. We assume that this function is sine omega t, and you make derivative once and use chain rule. By chain rule, it is equal to sine omega t d sine omega t, d omega t. We treat the omega t as a variable, okay? But the variable is actually t. Therefore, you need to be multiplied by chain rule by the omega t over dt. Okay, 这可以吗？哈。Okay, so but omega t dt is equal to omega. Okay, so sine omega t, if we treat the omega t as a variable, like you call it theta, then this is sine theta over d theta. Sine theta over d theta is cosine theta, right? Okay, according to your calculus class. So cosine theta, let me put it back, is cosine omega t. Done. So d sine omega t dt is equal to omega cosine omega t. This is a very, very important calculation. If it's easy for you, good. If it's not, try to understand every detail of this, every step of this calculation. Okay. Usually, when I do, I will just thinking in my mind, sine omega t over omega t. Oh, it's cosine. Then omega, put the omega in front, because the variable is t, not omega t. So this omega needs to be pulled to the front. That's the second term. That's the second term of the chain rule. Okay? So the first derivative has been calculated. How about second derivative? Second derivative, I will do this over dt. Okay? Then the same kind of reasoning will go again. I treat d cosine omega t over dt by chain rule is equal to cosine omega t over d omega t, which give you sine omega t. Sorry, negative sine omega t. And then I put times by chain rule. It need to be timed by omega t over dt. And omega t over dt is equal to another omega. So there is a omega in front. Now the second omega, so it's omega squared. Okay. It's quite in detail, but I hope everybody will understand this equation. You can do it your own way anyway, but you have to be able to do it. Okay, so now the result. The result is that the sine omega t second derivative is equal to minus omega squared sine omega t. Exactly what we need. That's why, remember this omega squared. That's why I put in the solution as sine omega t instead of sine t, because I need this omega to account for this omega squared in the original equation. If I do sine t, then there won't be any omega to appear in the equation. Okay. So this is by design. It's not accidental. So I write the answer sine omega t. Okay. And any question here? So sine omega t is one solution. We got one solution already. And of course, you will say that if sine is a solution, why not cosine? Of course, right? Because cosine and sine are twins, so they behave so similar. We almost put them together when we do discussion. Therefore, it is easy to show, you can do it on your own, the cosine also satisfies the same equation. So cosine omega t dt squared is equal to minus omega squared cosine omega t. Okay, so now we have two solutions. Okay, it's two solutions. Of course, this simple fact can also be done by using this so sophisticated mathematical technique we call Vrankian. Remember, in the first part of our highlight, we say that if you got one solution y1, you can get another solution y2 by this formulation. If you don't remember the derivation, forget about it. Just follow this. Remember, in our exam, you can bring in one piece of paper with calculation with formulas. Okay, so you don't really need to remember this complicated mathematical form. You are not going to use it very often in your future study. So I don't want to burden you with this memory. So so just write it down. Okay, so if you got y1, then y2 is equal to y1, da 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 da. Okay, but it's good to practice once, because we now have y1. Now why not we get y2 from y1? The sine function as y1. Could we get cosine? You can just by guess, but why not try? So in this example 7.63, that's in our Octagon textbook, you really quickly assume y1 equal to sine x and apply it to the simple harmonic motion, equation of motion, and you can see that immediately p is equal to 0, right? So p is equal to 0, then the exponential function is just equal to 1. Okay, so you only need to do the integration of y1 squared. y1 is sine, so it is sine squared x. Do integration and times sine. So I hope you can see the correspondence here. And if you do the integration, it's not very easy. So you have to go back to some probably ChatGPT. So you can see that this integration is equal to minus cot x. And then sine x times minus cot x just equal to minus cosine x. So this is a sophisticated way to get the second solution, cosine. Okay, so we have one solution, we have two solutions. I told you, for this kind of linear equation, we got infinite number of them now. So C1 y1 plus C2 y2, also the linear combination of y1 and y2. Now y1 is cosine and y2 is sine, in reverse. y1 is sine, y2 is cosine. So this combination will satisfy the equation also. Okay, so it's simple, and the derivation is here, just as earlier, and we know that C1 and C2 could be used to determine, could be determined by the initial condition as usual. Okay, so finally you have solved, okay, so sine omega t, cosine omega t are two solutions, and if we form a linear combination of them. Here I use A and B instead of C1 and C2. Okay, A cosine omega t plus B sine omega t. Then we found infinite number of solutions, and they can be defined. They can be determined by initial condition. I'm going to pass this part quickly because I hope Professor Liu has already covered in the general physics. Okay, I want to go quickly into damping oscillation. Okay, so x0 will determine A, v0 will determine B by this formula. Okay, so the general solution now, becomes x equal to x0 cosine omega t plus v0 over omega sine omega t. Okay, the point is not the form itself. The point is this form will satisfy both the equation of motion and initial condition. And it could be proven by the mathematician that it can be proven there's only one such function. So you have found it, you no longer need to search elsewhere. Okay, just one solution, and it is this one. Okay, we're done with solving the simple harmonic motion. Any question? And yeah, and this form is easier for the solving equation of motion, but usually you would like to combine the two terms into one cosine omega t plus phi. So in this form, but the mathematics are the same. You can find the very correspondence between xm and phi and x0 and v0. Okay, so these two forms are equivalent. And so that means simple harmonic motion is a sine function or a cosine function. That's the basic result. Okay, that's the basic result. And some diagram so that you can see the simple harmonic motion in motion. Okay, and here I have a list of the physical meaning of all the constants. For example, xm is the amplitude. Omega, so-called angular frequency, is 2 pi over t. If you are not familiar with any one of the facts here, you better check the PowerPoints. But it is usually covered by the general physics in the first semester. Okay. So omega is equal to 2 pi over t. That's why it's called angular frequency. Angular frequency. Because if you write omega as 2 pi f, then this f is just the times the times of cycle that happens per second. Okay, so that's f. Okay, and we don't need this. And this phi is a phase constant. That means if you use this kind of imaginary circular motion to imagine a simple harmonic motion, because there is a correspondence between this circle motion and simple harmonic motion. And then this phi is the starting point, the starting angle of your the angle of your starting point. Like these arguments, I hope you will understand it by your own. Now, 5 more minutes, we'll have a break. Now, we have done with simple harmonic motion. But usually, this kind of simple harmonic motion in nature, it won't oscillate infinitely. It will stop sooner or later. That means in nature, there are some dissipation of energy by resistance or whatever. So usually when we talk about a real simple harmonic motion, we usually introduce a term which is a resistance. Okay, resistance means it will resist the motion to occur. So this kind of resistance is very similar for the simplest kind. For an approximation, we usually introduce a term that is very similar to air resistance. Remember when we at the beginning of the semester we talked about air resistance. In air resistance, the resistance force is proportional to the first power of speed. We'll do the same here. Okay, it's approximation, but it's typical. So this term we'll call damping or resistance, whatever. Fd is equal to minus Bv. This B is a constant, negative sign because it's a resistance, and it's proportional to the speed. With this kind of resistance introduced, then the equation of motion will have one more term. Okay, this one more term is negative B dx dt because V is dx dt. Everybody. So let me introduce the second motion today. It's called damping oscillation or damping oscillation. Okay, here we have a damping force to resist the oscillation to continue infinitely. Okay, so this is the equation, and usually we would like to draw a diagram like this, because here we have a spring, we have a mass, and then if it is resisted by a resistant force of the liquid, then the equation of motion will be like this. It's easier to imagine a picture for your equation of motion. Okay, so damped oscillation. First step, we still move the m to the right hand side and push everybody to the left hand side. So it becomes d squared x dt squared plus b over m, because b divided by m, so b over m dx dt equal to, this is the same, k over m, so it's omega squared, but it pushed to move it to the left hand side, it becomes plus omega squared x. Everybody could see that. It is a typical homogeneous second order linear ordinary equation with constant coefficients, right? Okay, so that's why I introduced first earlier that I will add one more term so that the equation of motion will resemble this typical form exactly. Okay, now I have 1, 2, 3 term, 1, 2, 3. A second derivative, a first derivative, and a y itself. And no source term, so the right hand side is equal to 0. Later, of course, you know that what my intention. Later, I'm going to introduce a source on the right-hand side, but that's later. Okay? So now, y prime, double prime, plus a1 y prime plus a0 y is equal to 0. Homogeneous equation, damping oscillation, whichever way I call it. And wow. Now, a single sine function, a pure sine function or cosine function, could not satisfy this equation now. Remember, if I guess the answer, the solution is a sine, then if y is the sine, y double prime is the sine that we already know. But y prime is a cosine. There is no way to equate a sine and a cosine function, right? Let me put it in Chinese. 你不可能用一个 sine function 正弦函数来得到解，因为没有错，正弦函数呢两次微分还是正弦函数，所以这个是正弦函数，这个是正弦函数，可是 y prime 是余弦函数。Okay, so we're dead. Okay, so the simple conclusion is that pure sine function cannot satisfy this equation since first derivative will generate a cosine. Or if it is a cosine, pure cosine, then this first derivative will we just introduce the first derivative. Then this first derivative will generate a sine function. What now? Method 0. I'm going to go quickly through this method 0 because next week I'm going to introduce a systematic way. So if you don't like this pure mathematical calculation, just ignore but in this page, okay? But however, here you can see that by intuition, we could also solve this question. Method 0. Method 0, the intuition is, just look at this picture. What will happen? 物理学家的直觉, the intuition of physics. What will happen to this guy? Well, it will still oscillate, right? But it will go smaller and smaller and smaller and smaller. By smaller, I mean the amplitude will decrease. Oh, okay. So how about a brave guess? Still an oscillation. We call it cosine omega prime t plus phi. But the amplitude will be a function of t. Intuition. Intuition is very important to physics. Sometimes you don't need to go into detail solving and doing mathematics, but by intuition, you get the answer, you can guess the answer, and then comes back to prove it. Here, I guess. Because it's so obvious, right? You know what happened in nature. So again, what happened in nature is this guy will still oscillate, but because of resistance, the amplitude will decrease. So the amplitude will be a function of time. Okay, so now let's see what happened if I guess the answer is ft cosine omega prime t plus phi. Of course, I don't know what f is. I don't know what omega prime is. But by putting this equation, by putting this function into the equation, I'm going to solve ft and the omega prime. That's the plan. Okay, so let's see what happened. But I say the detail, I will go quickly. You can do it on your own, or you can just ignore this page. If I put in this into this term, it's easy. It's just the same. If I put this into the second term, now you see the difference now. It's a cosine function. By taking first derivative, it becomes a cosine function and a sine function. But of course, by chain rule, if it is a cosine function, then if it is a sine function, then f will not take derivative. But it's a cosine function, then f will take derivative by not chain rule, sorry, multiplication rule, right, in calculus. So from here to here, just plug in this function to take the first derivative. Originally, the function is a cosine function, but now it contains because the f, the amplitude, depends on time, then it generates a cosine and a sine. Okay, do it again. So if I plug in into the second derivative, well, the calculation is more complicated. That's why I don't want to show it on the blackboard. But you can do it on your own and show it is still a cosine function and a sine function. So probably some students have already know how I can solve the question. Because there are three terms. Each term contains a cosine and a sine. So if I can demand all the coefficients of the sine to be equal to 0, I ask the coefficient of the sine to vanish, and also I ask the coefficient of the cosine to vanish, I get two conditions. And these two conditions is enough for us to determine what f function is and what omega prime is. Get my point? 好 ，Let me put it in Chinese. 这个 function 呢，因为你的这个 amplitude 呢跟时间有关，所以呢，当你做微分的时候，不是只有 cosine， 它还会有一个 sin。两次微分也一样，有一个 cosine， 有一个 sin。哇，那就好了。刚刚的问题不是你的问题里面只有两项是 cosine， 一项是 sin， 所以没有办法等在一起嘛，对不对？因为只有一个项是 sin 嘛。可是现在如果每一个项都有 sin， 每一个项都有 cosine， 那你就把它们的 coefficient 解出来，解它的 coefficient 是等系数为0，当成是条件，你就可以写下两个方程式。Okay, so we put these two conditions, asking the coefficient of sine to vanish and the coefficient of cosine to vanish. Then we get two conditions. The first one, 2f prime equal to minus b over m times f. By this, I can decide the function f. It's a decay equation. It is just the decay equation. Okay, so f function is equal to xm times exponential minus b over 2m times t. Almost like decay equation. The solution of the decay equation. Omega prime, if you ask the coefficients of a cosine to vanish, then you get this formula, this equation. And this equation tells you omega prime squared minus omega prime plus b squared over 4m squared is equal to 0. Okay, therefore you can solve omega prime is equal to square root k over m minus b squared over 4m squared. Oh, so we got a solution exactly like our intuition. It's an oscillation. And the amplitude will decrease. And by mathematics, I can tell you how fast it decreases. It decreases exponentially. The amplitude decreases exponentially, like this. I go very fast. That's because next week I'm going to show you a systematic way to accomplish the same thing. So you just take a look, enjoy it, but you don't really need to remember it. By this page, I only show you intuition sometimes work. Okay, 好，下礼拜我会给你系统性的方法，所以呢这一页你可以看看就好。Okay, 好 ，but hope before next week you can be convinced that the oscillation of damping oscillation, the amplitude will decrease, and omega prime will be equal to the square root of k over m minus b squared over 4m. So this damping oscillation has two physical results, very prominently, two physical results. First, it is an oscillation. We know that already. And the amplitude will decrease exponentially. And if you see clearly, you write down the angular frequency of this oscillation, it is omega prime instead of omega. Omega is square root of k over m, right? So omega prime is square root of k over m minus b squared over 4m squared. So you see, if there is no b, there is no resistance. It is exactly like the ordinary simple harmonic motion. But with b, omega prime is smaller. That means the period is longer than usual. Okay, so omega prime angular frequency is smaller than damped simple harmonic motion. Okay. Oh, I think. Oh, sorry. I think. Oh yeah. I think let me show this first. So here you can see that, and you can also see that if B becomes larger, the resistance. If you increase the resistance, then omega prime will become smaller and smaller. In reverse, that means the period will become larger and larger. Here, I show two diagrams. The red one is a larger resistance. The blue one is a smaller resistance, weak damping. Okay, and then you can easily see in the first several cycles, you could not see very clearly. But after longer and longer, you can see, just me. From here to here to here, this is the second period. And the blue one is, yeah, so you can see that the blue one, the second period is here, but the red one, the second period is here. So the larger the B, the period becomes larger and larger. Okay, that means it oscillates slower and slower. Okay. And also here, I also show if B is larger, then the amplitude will decrease faster. Okay, weak damping, strong damping, and for strong damping, it just decreases very rapidly. Oh, here I think I have a motion picture. That's a simulation of what really happened. Okay, in this motion, in this cartoon, you can see that a spring will undergoing damping oscillation. And if you concentrate on the blue line shows an oscillation with decreasing amplitude. Okay, so it's really what happened in the nature. Before we have a break. This answer is beautiful. It's answer beautiful. Of course, I'm going to show you a systematic way of solving it. So wait until next week. But have you noticed something very weird? I say that omega prime equal to square root of omega squared minus b squared over 4m squared. So the larger the b, the smaller the omega prime. But if you increase b little by little, little by little, little by little, at a certain point, omega prime will be equal to 0. Yep. When b squared over 4m squared is equal to k over m, then omega prime is equal to 0. What do you mean by omega prime equal to 0? That means it does not oscillate anymore. It does not oscillate anymore. So, when I say damping oscillation is oscillation, I'm cheating. I mean, it's a half-truth. If the damping is not large, then it oscillates. But if a damping is large, just stop oscillating. It becomes an exponential decreasing function. Again, I will show you by systematic way next week. But let me show you maybe a cartoon. Okay, so this is for the same simulation, but with a larger resistance. You can see that it never finished one cycle of oscillation. So this spring simply stopped. Ladies and gentlemen, damping oscillation. No, there's no oscillation, only damping. Just stop. So it's okay. Then here I show three. So obviously, which kind of phenomenon will happen depends on B. When B is large, then it becomes exponential decreasing function. When B is small, it remains a oscillation with decreasing amplitude. Bingo. Okay. So next week you will be able to see how these two kinds of solutions will appear simultaneously at once from our systematic way of solving it. Okay? What else? Okay. So we're going to have a break. After the break, I'm going to introduce the force, the external force, which we will call force observation. Okay. So let's have a 10 minutes break. 是不是有人要交作业？我刚刚看到有，还是你？没有。好 ，OK， 那记得要交在网络交哦，哈。